Alrighty, welcome back to topic 11.6. This is Kirchhoff's loop rule, and this is daily video 2, where we are going to learn the rules for making Kirchhoff loops and apply them to circuits without any junctions in them. Again, my name is Dr. Kelly Miza. I'm from Delaware Valley Regional High School in Frenchtown, New Jersey. So first off, let's review. So last time we said that a complete loop around a circuit has a potential difference of 0. If you end where you start, your total change in potential is 0. So today we're going to put that to work by writing out our Kirchhoff loops for a specific circuit and then using that loop to solve our circuit. So there's some steps we like to follow, or I personally like to follow, I should say, in order to write our Kirchhoff loops. So you want to choose a starting point, and your loop that you're going to follow has to start and end at the same point. Then you're going to sketch in your currents for each little branch of wire. The direction that you draw these currents doesn't matter, because if you're wrong, your problem will tell you that you're wrong by giving you a negative sign, telling you it's actually in the opposite direction. And we'll see some examples of this in the future as well. Then we sketch in our loops. And now we're going to follow our loop and add or subtract the voltage contribution from each piece as we go around. So I made a handy dandy chart in order to tell you if this is positive or negative contribution. So if we encounter a battery while we're following our loop, and we go from the negative terminal to the positive terminal, we are getting a boost from that battery, so we are adding to our voltage. However, if we are going through our battery backwards as we follow our loop from positive to negative terminal, we take that as our battery's kind of holding us back. It's working against us. So we're going to subtract that voltage from our loop equation. If we encounter a resistor where our loop and our current are following the same direction, resistors take away voltage from our loop. And if we go through a resistor in the opposite direction that we have drawn our current, we're going to add that voltage contribution. And this is going to make a little bit more sense when we actually go through it. Okay, so let's do an example. So first we're going to choose our starting point. So here's our beautiful circuit. We have a battery and 2 resistors. I'm going to start here. I like to start in the bottom left corner. That's just me. You can start wherever you want. It doesn't actually matter. I'm going to draw in a current. So I'm going to be like, my current goes this way. It goes nice and clockwise through our circuit. Sounds great. Then I'm going to sketch in a loop. So I'm going to start at my starting point where my little star is at, and I'm going to follow a loop all the way around until I get back to my starting point. Now, I'm going to follow my loop. So as I start at my star and I travel along my circuit in the direction I've drawn my loop, I encounter a battery, and I go from the negative to the positive terminal. So that gives me a positive voltage contribution. So I wrote that as a plus V over here. And then I go do 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 do, and I hit a resistor. I hit resistor number 1. So because I'm going through this resistor in the same direction that I have sketched my current, I'm going to subtract that voltage contribution from resistor number 1. And then I'm going to go do 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 do, and now I hit resistor 2. Same deal. We're going in the same direction as the current that I've sketched. So I'm going to subtract that voltage contribution. And now we're back to where we started. And since we ended where we started, this is equal to 0. Remembering Ohm's law, voltage across a resistor, V equals IR. So the current times resistor number 1 and current times resistor number 2, I'm going to make that substitution in there. Now these guys, because they're all in series, they all have the same current. So I'm not going to put any labels on my I. It's just I. And this is great because they have the same I. So I can factor out a negative I. So I get R1 plus R2, which then lets me solve for the voltage is equal to I R1 plus R2. But that's what we would get if we treated this as just 2 resistors in series. The series resistors, you add them together, right? It works like we expect. That's great. Cool. But what happens if you have 2 batteries? Dun, dun, dun. We can't just make series and parallel resistors, which is unfortunate, But now it's great because you have tools to deal with it. And that's a Kirchhoff loop rule. So we're going to start with finding our starting point. Tick, tick. I'm going to choose there. Again, down bottom left corner. We're going to sketch in our currents. The direction does not matter. So I'm going to go clockwise again. Then we're going to sketch in our loop. I'm going to go clockwise again. I like clockwise. That's just me. And now we're going to follow our loop. So I'm going to start at my little star. Now I'm going to go do, 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 do. I hit battery number 1. I go from negative to positive. So I'm getting a boost from my first battery. So I get a positive V1. And then I go do, 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 do. I hit my resistor. I go in the same direction as the current. So it's going to be minus my voltage across my resistor. Do, 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 boop. And now when I hit battery number 2, I hit it at the positive terminal and I go to the negative terminal. So I'm going to subtract that battery contribution because it's working against me as I travel through the path. And then I get back to where I started at my star. So all of this is equal to 0. Now, if I make my Ohm's law substitution, V equals IR for my resistor, bink, bink, and rearrange this a little bit by adding that to the other side, this behaves the same way as if I had V1 minus V2 contributing to the entire circuit, which is pretty neat. So if you have batteries working against each other, you can just subtract them if they're in series. So let's do a practice. All right, so we're going to take that same circuit, but I'm going to flip the direction of battery number 2. Let's derive an expression for the current through the resistor is what we want to do now. I'm going to make my starting point. There's my star. I'm going to sketch in my current, floop, clockwise. I'm going to sketch in my loop, floop, clockwise again. And I'm going to follow it. Just like last time, I'm going to go bloop, get a boost from battery number 1. So negative to positive gives me plus V1. Do, 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 do. Hit my resistor, minus IR. So I skipped that Ohm's law step this time. Once you get the hang of it, you can do that too. So minus IR through this resistor. And then when I hit battery number 2, this time I'm going from the negative to the positive. So I'm going to add it this time because it's helping me along my path. And then I get back to where I started. So all of that is equal to 0. All right, now since our goal was to derive an expression for the current through the resistor, we're going to solve for I. So I'm going to move all my V's to the other side or my IRs to the other side, however you like to do your algebra. So IR is V1 plus V2, which means my current is V1 plus V2 divided by R. Neat. So since my batteries are both helping my current around my circuit, I add them together this time. Okay, so earlier I said that the direction that you sketch your current doesn't actually matter. And I'm going to show you what happens if you draw it the wrong way. So let's do the same problem, but this time let's have our current going the opposite way. So I have my starting point, and I'm going to do my current counterclockwise this time. But I'm going to follow my loop clockwise like we did before. So if I follow my loop, I hit V1, so I get that boost. But this time when I get to my resistor, my loop is in the opposite direction that I have drawn my current. So that gets a positive voltage contribution from that resistor. So since I'm traveling in the opposite direction of the current, I get a plus IR. And then I come to my battery number 2, negative to positive, that's a boost. So that gets a plus V2, and then back to where I start equals 0. Okay, so let's do the same thing. Let's solve for I. So if I subtract my V's to the other side, my current is negative V1 plus V2 over R. So we get the exact same answer, just with a negative sign. So whenever you solve Kirchhoff problems and you get a negative sign on your current, that just means it's actually the opposite direction of how you drew it. Okay, so what should we take away? So Kirchhoff loop rule in particular, helps us solve more complicated circuits that we can't solve with just Ohm's law alone. And these are usually what you're going to use when you have a situation with more than one battery. So again, if you're going from negative to positive on a battery, that gets a positive voltage contribution. It's helping you along your loop. If you're going from positive to negative, you get a negative voltage contribution. It's holding you back. If you go through your resistor in the same direction as your current, you get a voltage drop. And if you go through the resistor in the opposite direction that you drew your current, you get a voltage gain. And that's it. Thank you.